Good morning, Math 3. I am here in my art studio. I'm going to do a little project today, and my goal is to introduce you to what you need to know to complete our final project for Math 3 for this year, 2020. So, I'm going to give you some examples, I'm going to show you some demonstrations, I might even show you a couple of things not to do, and we'll try to make it a fun and accessible process. We have really 1 week left of math, so we want to make the most of it. For the better part of the year, we have dealt with linear functions in one way or another, right? A linear function is a t-table, x and y, coordinate pairs that go on the coordinate plane and form a line, right? Linear function, linear equation, you should be able to hear the word line in the bigger word linear. Now, even though we've looked at this all sorts of different ways, we really haven't done a whole lot with where linear functions show up in the real world. Sometimes math can seem so abstract, right? Equations for equation's sake, and those are beautiful and fascinating, but we really want to get down to what actually happens in the real world and how we can apply some of what we've learned to do useful things. So linear equations show up most often when we need to measure, especially when we're measuring something related to time. Linear functions show up an awful lot in physics and in science in general. And so we're going to conduct a physics experiment, each of you in your own way, in your own home, practicing safe social distancing. Don't forget to wear a mask. And you're going to record some data to make sense of and create a math picture of what you have measured. So, have fun. Here we go. You need a ramp. This book is a good example of a ramp because the cover will lift up at different angles. I can measure how high off the ground it is or is not and control the slope. Ooh, there's one of those linear equation words. This cutting board could also be a ramp. Again, I can lift it up to create a steeper slope. I can lower it down to create a less steep slope. It is a hard, consistent surface that I will be able to roll something off of. This bowl is an example of what not to use. This will not make a good ramp. Wonk, wonk. A piece of cardboard could work well. A piece of tag board is too flexible and it will not give you consistent enough results because it bends. Step 2 is to choose something round that will roll. This marker would roll nicely. It is round on all sides. It does not have anything that will catch or obstruct the rolling. This marker will not work well. It's going to catch. It's not going to roll consistently with the cap on. Okay? A pencil will work well, but a mechanical pencil will not. Choose something round and cylindrical, like a marker, that will roll well. You need to find a ruler so that you can measure. In particular, I would recommend a ruler that starts at 0 right at the end so that you will be able to measure accurately starting at the floor. Other things that might be helpful include a longer tape measure to stretch out along the floor, some kind of tape to secure your ramp, and something that will let you set different heights for your ramp. These are tiles, but you could use books or something else that you can stack up and change. If you're all ready for your experiment, it probably looks something like this, and you have a long straight section of floor or table where you can roll things out. We are ready. Here we go. Start with the top of your ramp about 1 inch off the ground. Tape the front of your ramp in place so that it can't slide. Mark a starting line. If you're going to use a tape measure, make sure that it lines up with the very bottom of your ramp. Give it a roll. Clearly, this part of the experiment will take a little bit of estimating. Based on where the marker landed and the tape measure, I'm going to go with 37 1/2 inch. Now that we have data, we need to make a T-chart. Remember that X's go on the left-hand side, Y's go on the right-hand side, and typically along the X-axis, we would record something like time, but in this case, there's no time measurement, and so it makes sense to record on the X-axis the thing that stretches out the longest in a horizontal direction. So that is how far the marker rolls, okay? And we decided that was 37.5 inches, okay? For the Y of the coordinate pair, we need to go back and look, unless we remember, how tall the ramp was off the ground. In this case, it was 1 inch off the ground. This creates our first coordinate pair. So you can see I've added a few data points to my table. Every time I move my ramp up 1 inch, the marker seems to roll further, 3 inches, 67, 4 inches, 77. Might be a linear relationship, I won't know until I make a graph, but I ran into a problem here. When I raised my ramp up 5 inches, my marker ran into the wall. I'll show you. What will we do? Is this a tragedy of modern experimental physics? Can our brave hero find a way to circumnavigate the impossible? Why, yes. Yes, he can. And here's how. So, I have put here that you need at least 10 experimental data points. This is non-negotiable. You've got to have at least 10. Over here on my table, I can see that there's no way I can get 10. In fact, there's no way I can even get 5. I'm gonna make a note right here. Hit wall, wonk, wonk, okay? But what I can do is go back to my ramp and make smaller adjustments. Chances are good in your experiment you will have some issues too. Maybe it's a bump at the sidewalk, maybe it's the fact that the floor that you're rolling across isn't actually level, and at a certain point it starts sloping downhill or uphill and affects your experimental results. That's okay. You still have to get 10 data points in, and so I would suggest smaller moves. For example, 1 inch of change for my ramp is the same as 2 tiles. Maybe you're gonna use books, it's up to you. But if I have measured every inch, right, every 2 tiles, I could go back and run my numbers for every half of an inch. That will double the number of data points that I can have. So now I need to make my t-chart bigger because I'm going to run this for 1.5, 2.5, 3.5, 4.5. I forgot one. I should run it for 0.5, half of an inch. And now I'm at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 data points. For this one where I hit the wall, I can go over and look. I think the wall happened at about 113 inches. And even though that may be incorrect, I will put in what I measured along with that note that I hit the wall. And that will get me my 10 data points. So here we are in Autodesk Sketchbook. You can certainly do this on an actual piece of graph paper. I have used a copyright-free piece of graph paper from online that I will attach to the assignment so you can do the same thing. And I have created a y-axis, I've created an x-axis, and I'm going to start to think about my scale for making a math picture. When I look at my whole data set, my y values go from 1 through 5. They don't get bigger or smaller than 1 through 5. And here on the graph, I have created a scale that should work as long as the iPad doesn't run out of batteries. When I look at the information on the X side of the t-chart, I see that everything stretches between 14 and 113. So I probably need a scale that goes from 0 to 120. And that could look something like this. Part of the reason I don't write all of the numbers in is that the scale gets too crowded for easy reading. So I kept it simple: 20, 40, 60, 80, 100, 120. And now I'm ready to graph my points. So the lowest value that I have is 0.5 on the y-axis and 14 on the x-axis. That's gonna look something like this. My next biggest point is 1 on the y-axis and 37.5 on the x. So I'm gonna look here at the line that corresponds with 1. I'm gonna go over here and find 30, and then 35, 37.5 will be somewhere in between, and I think that should put us right in there. Now, it's important to remember that 2 points make a line, but not necessarily a linear function. So I wanna see all 10 points on the graph before I try to decide on a line of best fit. With everything graphed, our data set looks like this. And this is a pretty good example of what happens when we apply math to the real world. Data is messy, but we can still use linear functions to make predictions and accurately describe situations within certain parameters. So I'm going to select the ruler. It shows up right here. I can adjust it with 2 fingers, and I'm actually going to turn it until it fits my data. Okay, now remember, our rule of thumb for line of best fit is an equal number of points above and below the line should give us an approximate line of best fit. So I have 1, 2, 3, 4, 5, 6 below the line. I only have 3 above the line. I think I probably have to adjust some, okay, until I do a better job splitting that difference. But based on the line of best fit that I come up with, I will be able to create a linear function with a slope and a y-intercept that could help to predict other points along this line. That's enough for now. That will bring us to the end of part 1 of our project, the experiment, the data collection, and the math picture. In part 2, we'll take a look at the data and the math picture that you've created and use slope-intercept formula to create a linear function that best fits what actually happened in real life. In part 3, we'll take a look at the function that you created and at the experiment that you did and think about what went well, what could have gone better, and what you might do differently the next time you try to model real life with math. Thanks for watching. Make sure to ask lots of questions. I'm excited to see videos of the experiments that you create.